Hey everybody, welcome back. Here we are. So we have one conversion that we have not yet discussed. We've gone one direction but not the other. So we have looked at the geodetic to geocentric, and that is to say the geodetic being the latitude, longitude, and height. We have converted to XYZ coordinates, but we haven't gone the other way yet. So we've gone this direction. Now we're going to go the other direction. We're going to go from geocentric coordinates to geodetic coordinates. So we're going to convert XYZ, or Earth-centered, Earth-fixed coordinates, to latitude, longitude, and height. One of these components, converting to longitude, is less complex than the other two. So why don't we start with that? So for longitude, if we look at, consider going back, remember how we would look down on the pole? And when we do that, we're looking down on the equatorial plane. So that would be the X and Y axes. So if I draw out a set of X and Y axes, so there's a Y axis. Remember, this is a top-down view. And so we have our X and Y axes. And we have our Y-axis and our X-axis. And let's say that we have some point here. And if we consider the vector from the spin axis out to the point, then we have a vector like that, right? And this is top-down view. So remember, in a top-down view, this angle off of the x-axis would be lambda. So at x, lambda equals 0 degrees. Up here, lambda equals 90 degrees, and lambda equals 180. And down here, lambda equals 270. And these would all be east longitudes, right? And when we've seen this kind of situation before, well, we're just lambda is equal to, let me do it down here. I'm going to erase that. And okay, so we have the tangent of lambda equals y over x, right? So lambda is just equal to the arctangent of y over x. That's terrible. Let me rewrite that. I'm not off to a good start here with my writing, but I'll get there. So lambda equals the arctangent or tangent inverse of y over x plus c to adjust for quadrant, right? This is a little bit different than the azimuth problem where we are, we still have our quadrants 1, 2, 3, and 4. But since we are doing the y over x instead of eastings over northings, remember that the angle being returned is the angle relative to the x-axis. And this is done in a mathematical sense, so counterclockwise is a positive direction. So if it returns a positive angle, it would be returning this angle, which would be positive. If the vector instead were, I'm going to erase some of this so I can draw. Let's say the vector's down here. Then the arctangent would actually return this angle, and it would be a negative angle that's returned, right? Because it's clockwise. So just a little bit of a different, you're going to have to adjust from how we've used the arctangent in the azimuth environment to a more mathematical environment. So keep that in mind when you are constructing your longitudinal calculation. So for longitude, I'll write it over here. Lambda equals the inverse tangent of y over x plus some constant to adjust for quadrant. That being 0 degrees or 180, what have you. So longitude's pretty easy. Longitude is straightforward. We've done that 100 times, just with a little bit of a different culture to the problem, right? So we're going to spend a lot more time looking at deriving the latitude and the height from the XYZ coordinates. So if we are given XYZ coordinates, so given, let's see, given the Earth-centered, Earth-fixed, geocentric coordinates, which are XYZ, right? Cartesian coordinates. We need to calculate. We've already done longitude, so we need to calculate phi and h, or latitude and height. And we're going to do this with an iterative process. So I'm going to lay out the theory first, and then when I go into the example, we'll talk about choosing our values for our assumptions in an iterative process. So let me scoot this up to make some room. So we need to calculate latitude and height. And something that we need to remember with latitude and height is that they are dependent upon one another. That is, they are functions of each other. And just as a review, let me demonstrate that real quickly. So if we have the ellipsoid, so there we have our ellipsoid, and we have some terrain here. I'm exaggerating, but let's say I have a mountaintop, and I have a point on that mountaintop. And of course, I could project that point down to the ellipsoid, right? So the thing that we have to think about in terms of latitude is that the latitude of that point here, the actual point, is clear up here, as opposed to the latitude of the projection down to the ellipsoid. So the latitude is dependent on what height the point is at. From that, we can surmise that latitude and height are inextricably linked. That is to say that we cannot consider the latitude of a point without incorporating its height, because the latitude is going to be different if it's on the ellipsoid or below the ellipsoid than it would be if it were above the ellipsoid, right? That makes sense, and that's just review. So let's do that. We're going to develop the idea or the extraction of latitude and height together, and we're going to use that value, that radius of curvature in the prime vertical. If we'll remember that, what that is. So if we have our ellipsoid again, so ellipsoid, that's a terrible ellipsoid. That's more like a geoid, isn't it? And we're looking laterally, so here's the equatorial plane. And here's our z-axis. And this is a lateral view. What do we want to do here? Remember, so if we have a point up here and we throw a perpendicular down, so the perpendicular would be there. It's perpendicular to the curvature there. And we would extend it then to the axis, and we call that length n, right? And if you'll remember, n is equal to a over the quantity 1 minus e squared, or epsilon squared, times sine squared phi. Now, all of that denominator to the 1/2, or the square root of the denominator, that's our n. So we're going to use these concepts then to extract the latitude and height and go through an iterative process to perfect it to whatever degree of precision we like. And we'll also let me reiterate too that the latitude, the geodetic latitude, is right here. That's the angle between that radius of curvature and the prime vertical, or just the radius of curvature, the m value, either one. The angle formed by that vector and the equatorial plane is our latitude, our geodetic latitude. So remember, we went through some pretty lengthy and laborious derivations to get a couple of values. So we have that n value. I wonder if I can just grab that and pull it down. I think I can. I don't want to lose this. Just see if I can pull all that down. Yep, I can. Good. So we have our n, and from those laborious, lengthy derivations I did earlier in the term, we got tan of the geodetic latitude is equal to a monster. So z, the z value, or you remember we have x, y, z coordinates, that's the z coordinate, over the square root of x squared plus y squared, all over 1 minus epsilon squared, or the eccentricity squared, times n over n plus h. So the tangent is all of that. So we would take the inverse tangent to get the latitude. And remember, latitude goes from 0 to 90, so we don't have to worry about quadrants in that tangent inverse. So we can just take the tangent inverse, right? So we also have h, the height from xyz, is equal to the square root of x squared plus y squared over the cosine of phi, all of that minus the length of the radius of curvature in the prime vertical. So that should be more like that. There we go. So we have everything we need in order to extract that latitude and height from our XYZ coordinates. We're going to do that, an example, but first I'm going to walk you through the process. All right. So something about the iterative processes. Well, hopefully you have those written down and you can just refer to them because I'm not going to have room. So with an iterative process, come on, color, okay. With an iterative process, we usually start with some assumptions. And we know these assumptions are false, but they're a starting point. So false assumptions give us a starting point, and then we refine through the iterative process our solution to whatever degree of precision is required or that we desire. So we start with false assumptions, then we hone in, I guess, that's a good way of putting it, on a more accurate solution. Through iteration, or I'll put repetition. And we've seen that. We've done that with a couple other applications in this term, and we'll do it again in other classes. But to illustrate the iterative process, suppose we have coordinates, we have geocentric coordinates x, y, and z. The first step is we assume h equals 0. So we assume that we have a height of 0. So we're right on the ellipsoid. We assume that h equals 0, and then we determine n and phi, or our radius of curvature in the prime vertical, n, and phi, just from our formulae, which I'll write down again. Phi equals tan inverse of z over the square root of x squared plus y squared over 1 minus epsilon squared, eccentricity squared, times n over n plus h and then h equals 0. So if we're going to assume h equals 0, then h goes to 0, and n over n is just 1. So we just have our 1 minus epsilon squared. It simplifies things pretty substantially. So let me get some more room here. And so if we assume h equals 0, we're left with, I'll put, so phi equals, with h equals 0, that's our assumption, z over x squared plus y squared over 1 minus epsilon squared. And the epsilon, the eccentricity just comes from our definition of whatever ellipsoid we're using. We're going to use GRS 80 as we have been, but we could just as easily do this in the Clark 1866 or whatever ellipsoid we want. Remember, there's an infinite number of ellipsoids. We could even invent our own ellipsoid by establishing the flattening and the semi-major axis distances, and just create an ellipsoid on the fly, brand new ellipsoid. And we would use those components then to calculate the eccentricity. We have our x, y, z coordinates. So all of those numbers are known. There are no variables here. We can easily get a phi. So once we have that, then we can recalculate h. And we use that h value then, and the full, then this no longer cancels out. Then we can use that to get our new phi. Then we go through the process again. We just repeat, and it will zero in on the correct latitude. Iterative processes are really useful and pretty magical, I think. I mean, to start with something completely incorrect and then land on a correct value, I think is pretty mathematically strengthy. So then step 2. To illustrate the process, I think let's use an example. To illustrate the process, let's use an example. Let's say x equals negative 2490 000.000 meters, and y is equal to negative 4 020 000 meters, and z equals 4,267,000 meters. So x, y, z coordinates, geocentric coordinates of a point P. And then we also have our GRS 80. So I'll put up here, use GRS 80. And with GRS 80, the definition says A, or our semi-major axis, is equal to 6378137.000 meters. And the square of our eccentricity, again, just a definition, is equal to 0.0066943 800 2, 3. There we go. And remember the eccentricity, the semi-minor axis, the flattening, the 1 over flattening are all they're equitable, meaning that they all kind of are the same thing, just in different formats. So we could take the square root of this, the eccentricity squared, to get the eccentricity. From that, we could get the flattening. From the flattening, we can get the semi-minor axis, B. So this tells us everything we need to know about the ellipsoid. So these are just GRS80 definition. Okay. Now we just use the formulae. So phi equals the tan inverse of all that stuff, which we've written down several times. And if I just plug in those parameters along those GRS80 parameters along with the XYZ coordinates, I would get phi is equal to 42 degrees, 15 minutes, and 12 seconds. Well, 12 point. It's helpful in these iterative processes to carry the decimal places out quite a ways. I think 5 decimal places is sufficient for the latitude because you want to be able to see the change as you go through the iterative process. Okay, so now we have our latitude approximation. So this is an approximation. We know it's not correct, but we're going to refine it. So that was step 1. In step 2, using that approximation for phi, we want to calculate a new radius of curvature in the prime vertical and a revised height. So we'll actually be able to extract a more realistic height from that latitude than we started with. We started with a 0 height, which we know is not true. So remember, n is equal to a, which we have from GRS80, over 1 minus epsilon squared sine squared phi. And now we have a phi. Now we have a latitude to the 1/2. So we would calculate n. So once we plug in our values, we get n equals 6387811.565. And since we have our n, we can now get our height. So h, remember, from above, is equal to square root of x squared plus y squared over the cosine of our phi that we just got minus n. And when we do that, we get a value of 774.5004 meters. And again, it's helpful to see, I should probably carry that another decimal place to 5 decimal places so I can see where it starts to stabilize. But that's quite a bit different than a 0 height, isn't it? It's pretty amazing that we start with this assumption of a 0 height, and just after one iteration, we now have a more realistic height that's pretty darn close to the actual value. And we just continue, we just repeat the process. So step 3. So 3 Now that we have better values for N and H, we use the same process to refine the value of phi that we got, right? So we would say our phi2, or our next refinement, our next iteration, is equal to the tan inverse of z, that whole mess, z over x squared plus y squared to the 1/2, or the square root, over 1 minus e squared, or epsilon squared, sorry, times n over n plus h. So now we have a non-zero value for h. We can use that non-zero value in the full formula. And when we do that, we get phi2 equals 42 degrees, 15 minutes, and 12.31323 seconds. And look how little it changed. So we started with a height that was almost 800 meters short. We extracted a latitude, and the latitude we extracted was pretty close to that, wasn't it? So 42, 15, 12.39711. And now we have the same degrees, minutes, and integer seconds, and then just a little bit of change in the decimals. So then we just do it again. And again, and again. So now, step 4, we just repeat that process until there's no change in the latitude. So, or in other words, our phi sub n equals phi sub n minus 1. So our new we keep going, get a latitude, get a latitude, get a latitude, until we get a latitude that is of the same value as the immediately precedent value that for the latitude that we derived. And then, once we have that, once we have our phi, so let's say we have our phi, that we're satisfied is a close enough value, that is that we're not seeing changes out to the 5th decimal place. I'm not going to put step 5 yet. So going through that process, we have phi, so we have a phi1, a phi2, so phi sub 3 going through that is equal to 42 degrees, 15 minutes, and 12.31349 seconds. Phi sub 4 equals 42 degrees, 15 minutes. And notice that the amount that it changes is less and less each time. So 31349 seconds, and that we have a repeating value. So we could stop there, but just for kicks, we would go ahead and calculate a phi 5 to make sure it stays the same. We didn't make any mistakes. Minutes, 12 seconds, point, and it does stay the same through those calculations. So we have our latitude, and we're going to stick with that. So here is our good latitude. So we're going to say phi that we're looking for is equal to that value. So step 5, now use the final accepted fee to get our height, h. So using our formulae, h would be 772.1562 meters, of which I would just report 3 decimal places. But I'd want to check out to further decimal places. And then we use our lambda equals tan inverse of y over x plus c to adjust for quadrant, which equals 121 degrees, 46 minutes, and 27.11181 seconds. And if you wanted to, you could add a step 6, which is nice to do because we do have a tool we can use. 6. We can check the results against NADCON in the NGS toolkit. And that's it. Then we've gone from our Earth-centered, Earth-fixed coordinates then to our geodetic latitude, longitude, and height. Pretty simple. When you build your spreadsheet, and I'm going to show you the spreadsheet. So let's see, I need to make this fit a little better. There we go. So we start with our initial values, our x, y, and z, and then we have our ellipsoid parameters from which I have calculated the eccentricity and the square of the eccentricity. And since I was given A and I looked up F, then I just calculated those values. I could start with A and the eccentricity squared if that's what I'm given. But these are just the GRS 80 definitions. I have my formulae here, and I have my initial value. So I have that arctan of all that junk, and I extracted that. That's the same number that I had before, 42, 15, 12.39711. And here is the n value based on that. And in the first iteration, we're going to compute our height and use that height to get a new fee. Or actually, we're starting with 0. We're assuming a 0 and going through, and then we get our new fee, and from our fee we extract a new height and a new n. Then if you build those formulae right, then all you have to do is just copy and paste. So then you can just copy. Over here I have the radians of my fee. It makes the calculations a little easier. So if you can see, I'm going to go ahead and do that. What if I just wipe these out? I did build these in a way that would allow me to just copy and paste. And if you think about it, you can make it that simple. Make sure that you are rendering referenced cells as absolute or relative, depending on what you want. Okay, oops, I didn't want to. There. So the way I built this, all I have to do for my next iteration is just copy it, and then I can paste it. And the numbers update as I go. Oh, I did something wrong because, my numbers aren't coming out right. Something's wrong with my copy and paste. Okay, so the error that I made is that my initial first iteration references some cells a little bit differently. So I can't really copy this one, because remember, our first iteration we're assuming a 0 height to start with. So then I would build my second iteration using the equations. And once I do that, if I build it right and I reference cells as absolute or relative as is necessary, then I can just copy. And there we go. Just like that, we have our latitude, our longitude, we have our new n value, and we have our height, which should have come out the same as what I wrote down. And it did. Okay. Finally, we can use the NGS toolkit, Geodetic toolkit, and I'll show you how we do that, to get our latitude, longitude, and height, which are here. So if I bring up the Geodetic toolkit, the tool we're going to use, wish this thing would size automatically, but it doesn't, so there we go. And the tool we're going to use is the one we've been using for conversion, the NGS coordinate conversion and transformation tool. And we're going to go from XYZ to geodetic latitude and longitude. So I just picked that option and I put in my latitudes or my XYZ coordinates, which I need to find. So my X is minus 2490000.000, and my Y then is minus 402000.000, and my Z value then is 4267.000, and then I submit it, and hopefully if it all works out, look, there we go. And then I just use the snipping tool to cut that out, save the image, and then paste the image in my spreadsheet right here. And look how close the values are. They're exactly the same. That's pretty cool, considering that we started out with just a made-up number for our height. We iterated to get the proper height, proper latitude, checked it against NGS, and got the same values. Pretty cool. So this spreadsheet is posted. I did update my Excel version, so it looks a little bit different. But I did post the spreadsheet, this spreadsheet with the numbers on Excel. So again, you can create your iterative process and check the numbers based on this example, and then you can use that spreadsheet for conversions in the future. So this is on Canvas, and what did I miss? I think I hit on everything. That gets us through another part of the problem. So if you have any questions, come to a Zoom session or reach out and request a Zoom session. I'm happy to set them up whenever you like. And hopefully this will get you through everything on the homework except for the gravity stuff, which we haven't talked about yet. So let me know if you have questions, and I will talk to you later. Have a fantastic day.